Hello everyone, my name is Kathan and today we will be discussing the problem playlist from the sorting and searching problems of the CSES problem set. Let's begin. Let me read out the question for you. You are given a playlist of radio station since its establishment. The playlist has total of n songs. What is the longest sequence of successive songs where each song is unique? So basically you are given a list here which contains this music IDs, right? Song IDs. You want to find the longest sequence of successive songs where each song is unique. In other words, the song IDs are unique. So input here is simply a list of songs. So first they will give you n, the number of songs we have, and then they will give you the IDs of each song, k1, k2, so on to kn. Output, you want to find the longest sequence of unique song. Important is the sequence is consecutive, right? Longest sequence of successive songs. Fine. So here constraints are given. N is as high as 2 into 10 power 5 and k is as high as 10 power 9. Now, if you see example test case input here, n is 8, so there are 8 songs and these are 8 IDs given to us. You find me the longest sequence of successive song IDs which are unique. So if you want to see, this is the ID. So 1, 2, 3, 4, 5. So these 5 are the, you can say the longest sequence which has unique song IDs. And basically we just want to print the length of the longest sequence. They don't ask us for the longest sequence. So I mean that's about the question. Let's go to the iPad and try to discuss a bit more on this. First things first, let's talk about constraints here. So n was as high as 10 power 5. That is the number of songs that we are going to have. Now what it says is basically it was 2 into 10 power 5. What it says is you cannot do n square number of operations, because if you do n square number of operations you will have to do 10 power 5 into 10 power 5, which is 10 power 10 operations. So this cannot be allowed in 1 second time limit. In 1 second time limit you cannot do more than 10 power 8 operations, right? So what then, you can do n log n, right? You can do n or maybe less than that. So you will have to think in this way, like n log n or so on and so forth, right? So with constraints cleared out, let's see example test case and try to solve it. So I'll take the same example that was given to us. So n was 8, so we will be given 8 unique song IDs, not unique song IDs, we will be given 8 song IDs, right? So let me write down those song IDs. They were 1, 2, 1, 3, 2, 7, 4 and 2. So 1, 2, 3, 4, 5, 6, 7, 8. So we are given 8 song IDs. Now you find me the longest sequence of successive songs, right? Important is successive. We want the consecutive songs. Longest sequence of successive songs here, and tell me its length, right? So what is the longest sequence here of consecutive songs? So I guess I already showed you this one, right? So this one, right? So 1, 3, 2, 7, 4, right? Now this is the longest sequence which has unique songs. Like you try to find a sequence larger than this, you won't be able to find it, right? So 1, 2, 3, 4 and 5. So you have to print answer 5 basically. Why? Because the longest sequence with unique song IDs is 5. Fine. Now if you look at this question, what is this question asking you? Find me longest sequence of successive songs where each song ID is unique, right? That's what this question is asking you. If you think a bit, can you reframe this as a longest subarray having unique IDs? You can, right? So they told me to ask, they actually told me to find the longest sequence of successive songs where each ID is unique, right? So this question can be simply reframed. So I'll maybe write here, yeah. This question can be reframed as find me length of longest subarray with unique elements, right? So this both are one and the same thing. So why did I do this? Because I wanted to concretize the question a bit more. So now we are after length of longest subarray with unique elements. Okay, so what is subarray? A subarray is simply a contiguous part of the array, so that you already know. Okay, so now we look at the question in this light. Longest subarray with unique elements. Now how can you approach this then? Now what is a brute force here, guys? So let's talk about brute force approach before we go and discuss the optimal one. So the brute force would be to simply enumerate all these subarrays, right? And find the longest subarray which has unique elements, right? So the brute force says, can we just simply enumerate all these subarrays? This you can do. And how many subarrays are there? Like, if you know, we have total of order of n square subarrays. And how does this n square come? More precisely, you have n into n plus 1 by 2 subarrays. How? Because let's say if elements like this a1, a2, a3, so on. So all the subarrays starting with the first guy is simply first a1, then a1, a2, then a1, a2, a3. That is, we have 3 subarrays starting with a1. Similarly, we have 2 subarrays starting with a2. Similarly, we have 1 subarray starting with a1. So this is how we have order of n square subarrays. The brute force says go through all the possible subarrays we have and find the longest one which has unique elements. Like, how do you find a subarray if it has unique elements? Maybe you can use a map or a set, whatever, but the important thing is you cannot enumerate order of n square subarrays. This is not possible. We need to do something better than that. We have to start with n log n, right? N log n or n log square n, whatever. But n square cannot be approached. So brute force is out of the picture. If we cannot do brute force, then what? Now, if you've watched that maximum subarray sum question, the next idea that can come to your mind is, can I find longest subarray with unique elements at every possible index, like it's that every j belongs to 1 to n, right? Maybe if there is a way to find the longest subarray with unique elements at a given index, right? You can just take the max of all the results, right? So what I'm saying is, if you have a way to find longest subarray with unique elements at index 1, then longest subarray with unique elements at index 2, index 3, 4, so on. If you have it, you know there are just order of n indices, right? You have n indices, you will have to find the longest subarray with unique elements at n indices, right? Then you might be dealing with here order of n's complexity, right? And our answer will be simply a maximum of all of these subarrays, right? So that's one thing. Let's think in that direction. Then how can you go about finding longest subarray at a given index? Because if we have that, we might be able to deal with order of n or a little bit more than that complexity. Let's see. How can we approach this? Now we know that we are given some song IDs here, like K1, K2, K3, K4, so on, Kn minus 1 and Kn. Now these are the indices as well. Let's just call it 1, 2, 3, 4, n minus 1 and n. If someone asks you what is the longest subarray ending at index 4 with its unique elements, how are you going to approach it? Now we know that all the possible subarrays ending at index 4 will be 4. Why? 1, 2, 3, 4. Okay, that's one thing. You want, what do you want? You want longest. And you want all of them should have unique elements, right? Because our answer is simply maximum of every possible longest possible subarrays, right? That's our answer, right? So firstly, we want longest. Now, what is the longest subarray ending at index 4? It is simply this, right? Its size is 4. But this constraint that we want unique elements, how are you going to deal with it? Can you think about some greedy strategy here that we know that the longest subarray ending at index 4 is 4, fine. But now one more constraint is there, which should only have unique elements. How are you going to tackle that? So ideally you would want that all these 4 elements are unique. If these 4 elements are not unique, you maybe remove some elements, right? Maybe remove K1, maybe remove K2, then maybe you have to remove K3. Of course, an array with a single element will always be having a unique element. So in the worst case also the answer can be 1. So think about this. From this array, you can say this window of elements from 1 to 4, can you just remove, you can say the smallest portion from the start, which is causing duplicate elements. Again, you know the maximum subarray, you can say the largest subarray ending at index 4 has 4 elements. Now you want to ensure that we want unique elements, but you also want to ensure that this is as big as possible. So maybe from the start, we just remove that portion, like just enough portion, which still keeps the unique elements. This you can do, right? From this portion, if we remove just enough portion such that the remaining elements are unique elements, you got the longest subarray ending at given index with unique elements. I guess it makes sense. So let's try to concretize it a bit. Let's say, I'll give you an example here. Let's say we have 1, 8, 5, 1, 8, 5. Maybe let's say this is 7. And we got 1. Now, you want to find the longest subarray ending at index 1. Now, ideally, this would have been the answer, right? This would have been the longest subarray with unique elements. But you know this 1 is creating problem, right? So ideally, what I'm saying is, this could have been our answer, right? The longest subarray ending at this guy would be what? This was maybe 1, 2, 3, 4, and 5. So ideally, the longest subarray ending at index 5 should have 5 elements. But you know, duplicate elements are going to create problem. So what you do is, you remove the smallest portion from the start, such that if you remove it, you have unique elements remaining. This makes sense, right? So here, the answer will be 3. Fine. Now let's try to concretize a bit. You know, we have song IDs like this, K1, K2, K3, K4. I'll need some variables to keep track of where I am currently. So one variable I can put here. So what it means is, when j is equal to 4, I am looking to find the longest subarray with unique elements ending at index 4. I'll also need one more variable, like maybe here. What it keeps track is, so it may be at any place, but what it keeps track is, all the elements in this range are unique, right? So this actually keeps track of, I'm removing just enough element so that this portion is maximized, right? So initially they both will be equal to 0. Don't worry, you'll get it. Stay with me for a while. So I is 0 and j is 0. This means initially we both started here, right? And if you observe here, the longest subarray ending at index 1 is simply 1, right? With unique elements is simply 1. So maybe we can initialize our answer to 1, because in any which way you will have a array of size 1, right? Then what we do is, we sequentially process it, right? So when we want to find K2, we increment this j. Then we'll be considering this window, right? When you want K3, we'll put j here and we'll be considering this window. When you want K4, we'll put j here and we'll be considering this window. And from this window, I'm going to subtract just enough to get the maximum, like you can say, longest possible subarray, right? So what I'll do is, I'll expand the window from right one by one. So what does this effectively mean is, we just increment a j, right? So it's simply j plus plus, right? So at the next step, j will come here, right? Similarly, in the next step, j will come here, so on and so forth. So let's say after a while, j is here. Okay, we expand from right one by one. Okay. Now, what can happen is, when you expand, in the best case, this can be your answer. But when you expand, there might be a chance we have encountered, you can say, a duplicate element, right? For example, let's say this was 1, this was 2, and you encountered 1 again. So we have encountered a duplicate element, right? So what are you going to do? Remove the just enough portion such that we have unique elements till the current index, because whenever j is at some index, we want to find the answer for that index. Okay, so we expand the window from right one by one, that is for sure. And then if while expanding we have encountered a duplicate element, shrink the window from left till in this portion, that is this I to j portion. In this portion, I to j portion, we have unique elements, right? This makes sense. I guess it does, right? We expand j, we try to expand our window like this, and whenever a duplicate element is encountered, we just shrink the window just enough so that unique elements are maintained in this portion, right? And once we have, you can just shrink the window, we can update our answer, right? Can update answer, that is answer can be max of answer, whatever current value of answer is, and if this is, you can say, the bound, you can say this is the this is where you are trying to find your optimal answer, and you know that in I to j you have unique elements. What are number of unique elements here? Like, what is the longest subarray ending at index 4 with unique elements? It's simply whatever number of elements you have here, that is j minus I plus 1. Or simply, if you are keeping track it using a map or a set, you can simply have it as its size. So we are not talking about implementation as of now, but that's what you have to do. So maybe you can just separate it by j minus I plus 1. That's that. Now the strategy might be looking a little bit vague, and it's understandable. Let's do a dry run and you'll understand it. Don't worry, stay with me for a while. Now, first things first, we need two variables here, right? Which basically are simply the bounds of the window. So initially, you know that the first window that you have is simply this, that is I and j both are initialized to 1. Maybe I can just write it above. So ij both are initialized to 1, right? And we know that our answer will also be initialized to 1, right? Because our answer will be at least 1, that's why. And what we need is whenever we process a new element, if you remember, what we do is we expand the window, right, as we go towards the right. So whenever we process a new element, we need to store it temporarily, right? So this window elements have to be stored, right? But there's one more thing, you also have to shrink the window, right? So what are you going to use for it? If you think about it, now you want actually this shrinking and expanding, right? So this should happen in constant time. So this gives you an idea. Maybe I can use sets and maps because they're very efficient in insertions and like in insertions and deletions. So maps or sets, these are the first thing that come to your mind. But temporarily we are also storing duplicates, right? So we are shrinking, right? So that is when I am processing these guys, temporarily both the ones can be present. So it might suggest you that maybe use a multiset or maybe a map. But I'll prefer using map here. You'll see why in a bit. But yeah, so we will use map here. Fine. So we'll use map to keep track of whatever the window elements are there. Okay. Then what? So we start from the first guy. We process the first guy. That is, in the window currently I have 1. So 1 is present one time. Fine. So 1 is present one time. So is there an element which is present more than once? No, it is not. Right? If it is not, then answer then update the answer. Since you can say the answer for this guy, that is the maximum, you can say longest subarray ending in index 1 is 1. Answer is already 1. It's not going to be updated. Okay. Let's expand the window. Let's expand the window. That is, now we want to find the longest subarray ending at index 2 with unique elements. Okay. Now that means once you have expanded the window, inner window, now you also have 2 present one time, right? So now this is how your map looks. Okay. Now is there a need to shrink the window? Is there an element which has occurred more than once? No, it's not. So now we update the answer. So initially the answer is 1, but we know in this window now we have 2 unique elements. Or in other words, the map size is 2. So yeah, answer will be updated to 2. Okay, answer is updated to 2. Okay, so now we have calculated answer for index 1 and index 2. Now we move ahead, right? So now we move to index 3. Now we want to find the longest subarray ending in index 3 with unique elements. Okay, first process this guy. Once you process this guy, one's frequency will become 2. Again, once you process this guy, one's frequency will become 2. Now in your window you have a duplicate element. So in this window you have a duplicate element. Now before updating the answer, you have to shrink the window from the left. Just enough. Just enough. Why just enough? Because we want the longest. Just enough such that we have again unique elements present. So how do you shrink the window? You move this I pointer ahead. So move this I pointer one step ahead. And if you move it one step ahead, frequency 1 will reduce. So frequency 1 is again back to 1. Now you have shrink the window by 1. And now again in this portion I to j you have unique elements present. Now you can update the answer. Now update the answer with what? Whatever number of unique elements you have in this range. It's simply 2 or the map size is 2. But so answer won't be updated. Fine. Now we have calculated the answer. Maximum, you can say the longest subarray ending in index 3 with unique elements. Okay, fine. Now we move ahead. That is, now I want to find the longest subarray ending in index 4. Okay. So once I have encountered 3, 3 will be added to map. So 3 will be 1. Now you ask me this question. are there, you can say, all the unique elements present here? Like, are there any elements which has frequency more than 1? No. So we update the answer. So answer will be updated to what here? You can say how many unique elements are there in this window? 3. Or the map size is 3. So yeah, answer will be updated to 3 as well. Okay, so we calculate answer for first 4 indices. Now we again move ahead. Now we move ahead. So it means 2's frequency will be 2. That is, you have just expanded the window. But 2 is present 2 times. 2 is present 2 times. Now what do you have to do? Remove just enough from the start. That we again have unique elements present. Remember, we don't have to start I from start again. We just moved I because of this 1, right? So we start from this I again. We try shrinking the window again. Okay, let's try to shrink the window by 1 here. So once you shrink the window, frequency of 2 will reduce. Again 1. So now, again in the window, you have all the unique elements. It means the longest subarray ending at index 5 will have 3 elements. These 3 elements. You'll try to update the answer, but it won't be updated. Fine. So we move ahead. Now, j is equal to 6. J is equal to 6, and in the window, now you have 7. So now you have 7. Okay. Now, is there an element which is present more than once? No, it is not. So the window size is 4, or you can say the map size is 4. So we'll update the answer to 4. We'll update the answer to 4. Okay. So now we have calculated answers for 6 indices. Right, now we move ahead. So that means 4 also enters. So 4 also enters the window. So 4 is occurring one time. Now, after expanding the window, was there a duplicate element found? No, it is not. So you update the answer. Answer is 5. Right. So how do you update the answer? J minus I plus 1, or like map also keeps track of number of unique elements. So map size, whatever. Now that is fine. Now we move J ahead. You move J ahead. So if you move J ahead, 2's frequency will increase. 2's frequency will increase by 2. So now, before updating the answer, you have to shrink the window such that you have removed just enough from the start, such that like you remove just enough from the start, such that all the elements in this range are unique, right? So we move I ahead. We move I ahead by 1. So it means 1's frequency will be gone. Right? So now you have no 1 in the subarray. Now you still have an element, you can say, you still have an element whose frequency is greater than 1. And how did you find it? It was simply the current element that you process, right? So the MP of, you can say, the array of j is greater than 1, right? So the current element that you just processed, it made sure that there was a element which was present more than once. You're trying to now shrink the window. You shrink the window once, but still that guy has a frequency. Of more than 1. So that guy's frequency is still greater than 1. So we have to shrink the window one more time. We come here. So now 3 is gone. But still 2 has a frequency greater than 2. Right? So you move ahead. And now finally, when I'm here, 2's frequency will be reduced. And the longest subarray, you can say, ending at index j, will have 3 elements. Will not update the answer. And after the end, like once j is gone out of bounds, we have answer. So this got you an idea that whenever you process a new element, you add it to the map, right? So MP of array of j, you do plus plus, right? So whenever you process a new element, there you do it. Now you just process the element, there is a chance that an element can be duplicated, and that element is no one but this one only. So once you have expanded the window just enough, you will just have to check while MP of array of j is greater than 1, you just shrink the window. Shrinking the window means just remove elements from the map, right? And what does this j do? This j simply goes from 1 to n. So I guess by looking at the dry run and these conditions, I hope you should be able to understood what we have achieved here. Right? If you did, please comment understood in the comments in the video, and then we can discuss the time and space complexity, and of course see the actual code also. But as a matter of fact, like, how about you try implementing the approach right now itself and maybe paste in the comment section. But yeah, let's discuss the time and space complexity here then. Now what did we do? Effectively, if you observed, there were 2 pointers which are moving, like I is moving from left to right, and j is also moving from left to right, right? But they are only moving once. the strategy that we developed only moves these two pointers from left to right just once. So definitely we are doing order of n operations there, and in each operation we are either expanding or shrinking, right? So we are either expanding, you can see, either adding something to the map or removing something to the map, right? When j moves, we add something to the map. When I moves, we remove something from the map, right? But we know all in all there are no more than order of 2n operations, right? And each one of those operations is either a map deletion or map insertion, so which simply causes log n, right? The size of map. So the time complexity turns out to be n log n, right? So that's one thing. And finally, what is the space complexity? We are storing, like you can say, the worst case, all the possible elements. So order of n space will be required. So this is the time complexity and this is the space complexity. So with that cleared, let's move on to the coding part and wrap up this video. Alright, so here's the code, guys. First things first, I'm taking the input n and the song IDs. Then I will create a map, right? I'll initialize my answer to 1 because you will have any which way a subarray of size 1 with unique elements. And then I'll initialize my I and j pointers both to 0. So this is 0 based indexing, that's why 0. Then while j is less than n, that is while we have not calculated the answers for every possible index, you first add the current element in the map, or you can say process this element, expand the window. While a duplicate element is present, shrink the window from the left, right? So mp of area of I minus minus, or if this element has frequency becomes 0, we just remove it from the map, and I plus plus, right? And after this is done, we know in the range I to j we only have unique elements. So update our answer with the length of map, or j minus I plus 1, one of them works. Now this length is not a standard function, I have defined it here. Okay, so I use a hash define here because, like, if you directly use x dot size, it will give you some sort of error because the data type of x dot size is different from integer. That's why you have to typecast it to integer. That's why I used to have a type definition of size operations. Fine. So you update the answer and then j plus plus, right? So why j plus plus? Because next time you'll have to process the next element. Okay. So after this loop ends, you will have your answer and you can just print it. The time complexity is n log n and space complexity is order of n dot 1, right? So because you will have to store all the elements in the map. And that's about this video. Like, so I hope you got something out of this video. If you did, please give it a thumbs up and I'll see you in the next one.